How would you deploy AI services using Docker containers? Deploying AI with Docker is like sealing your entire model environment into one reliable travel kit, so it behaves the same, no matter where it runs. You bundle the code, the model weights, and the exact versions of Python libraries, because even a tiny mismatch, like Torch 1.9 versus Torch 2.0, can shift predictions or spike latency from 30 to 80 milliseconds. In real companies like Netflix and LinkedIn, this consistency prevents silent bugs and unexpected accuracy drift. You build the image, push it to a registry, and let Kubernetes pull it instantly, on demand. A subtle beginner mistake is assuming Docker automatically handles CUDA. It only does if you explicitly choose GPU-capable base images. A strong interview answer is, I package the full inference environment into a Docker image, push it to a registry, and deploy it through an orchestrator for consistent, scalable service. A follow-up might ask about reproducibility, and you can say, the container locks the environment so output stays stable across machines. Don't worry if this feels abstract now. This part clicks fast. Why Docker for AI deployment? Let's make this easier to picture. Docker gives every model its own isolated workspace, like a dedicated bench, where no tools get mixed. But that isolation prevents conflicts when one model needs Torch 2.1 and another still depends on an older offset. Consistency means a model deployed today will behave exactly the same next week, avoiding environment drift that can quietly reduce accuracy by a few %. Containers scale fast. If traffic jumps to 5,000 requests a minute, you can launch 10 more instances in seconds. Portability means the same container runs on a cloud GPU node, a bare metal A100 server, or a small H box. A common mistake is thinking virtual machines offer similar agility. VMs often take 30 to 60 seconds to boot, while containers start in under a second. A clean interview answer is Docker provides reproducibility, isolation, fast scaling, and cross-platform portability. If they ask why that matters, you can reply, it lowers deployment risk and stabilizes model behavior. You're building solid instincts here. Nicely done. Step-by-step deployment pipeline. Now, let's peel this back like a smooth assembly line. The Dockerfile sets your base image, installs libraries, and copies model files, like prepping ingredients before cooking. Building the image creates layers that cache efficiently, so rebuilding after a small change feels quick, sometimes shaving minutes off CI pipelines. Pushing the image to a registry places it in shared storage where any node can pull it. Deploying means Kubernetes pulls that image to GPU or CPU nodes and begins serving traffic. Monitoring then tracks signals like inference latency, throughput, and GPU memory use. Say your latency climbs from 20 to 60 milliseconds, or GPU load sits at 80% for too long. A real-world pitfall is an oversized 8 gig image that increases registry pulls from 3 seconds to 20, slowing autoscaling and causing request backlogs. A sharp interview answer is, my pipeline builds a versioned image, pushes it to a registry, deploys with an orchestrator, and monitors metrics for autoscaling. If they ask how you automate it, you can say, CI pipelines rebuild and redeploy on every model or code change. You're putting the pieces together beautifully. Real production architecture. Now let's imagine real production flow, almost like coordinated trains on dedicated rail lines. An API gateway receives requests, a load balancer spreads them evenly, and model containers perform inference, whether it's ticket classification or genome similarity checks. The orchestrator keeps containers healthy, replaces failing pods, and enforces CPU, memory, and GPU limits, so one heavy model doesn't starve another. GPU-enabled base images ensure kernels run on accelerators rather than defaulting to slow CPU paths, which can drop throughput from 2,000 inferences per second down to a few hundred. Logging and health checks catch problems early, like a memory leak that appears after several hundred requests. A subtle beginner mistake is assuming the model is the bottleneck. In real systems, networking, cold starts, and GPU oversubscription often cause the most pain. A strong interview answer is, production AI relies on gateways, balancers, orchestrators, GPS-ready containers, and deep observability. If asked about scaling, you can say, the orchestrator adds replicas based on latency or queue depth. Common interview follow-ups. Versioning means tagging images like model v1.3, so you can roll back instantly if accuracy drifts by a few percent. GPU support requires the NVIDIA runtime, and you must declare GPU requests so the orchestrator assigns nodes with proper accelerators. Security means scanning images, because even one outdated base layer can expose the cluster. Monitoring watches latency, GPU memory, and drift. For example, if inference rises from 30 to 90 milliseconds, or if accuracy shifts over time, you'll catch it early. Rolling updates use blue, green, or canary flows to upgrade without downtime. A common beginner mistake is pushing images from local machines without scanning. Production teams rely on automated vulnerability checks. A crisp interview answer is, I use tithed images, GPU runtime configs, secure private registries, metric-based monitoring, and rolling update strategies. If they ask about drift detection, you can say, track output distributions and performance over time. Great job learning today. If this helped you feel clearer or more confident for your AI or ML interviews, tap like so more learners can find you. If you want simple guidance for every interview topic, subscribe so you never miss the next lesson. You can share your questions in the comments. I read them, and they help me choose what to teach next. And if you know someone preparing for interviews, feel free to share this with them. Keep going. You're improving with every step. I'm here to help you grow.